So today's talk can be considered maybe more of a history lesson, since I'm really just reading Poincare. And it's always interesting to see what these bright-eyed old guys did. Of course, this is one of his earlier papers, but he was still relatively young. Of course, he died fairly young as well. Okay, so let me start by sharing the screen with the text. Let's see. There we are. So what I wasn't able to do, I usually like to write things out by hand during the talks, but there's some very long formulas here that I didn't want to write out. And then I usually would then take the text and convert it into slides. But life is short and time ran out before I could do that. So I'm just going to use the text of my notes on this subject for this talk. So we had been, last week we talked about a so-called Positivstellensatz-September, which had to do with forms, homogeneous polynomials and n variables that were positive for positive or non-negative values of the variables. And at the end of his paper, Poincare writes something like this. Maybe I'll try to make it a little bit bigger. So this says basically the idea for this paper had some, there were like some special cases proved previously. The case for one variable was trivial, and the case for two variables was proved by Poincare. And it's this paper of Poincare published in Compte Rendu in 1883 that is the subject of this. And Poincare was a little bit puzzled, it seems, by Descartes' rule of signs. So you recall that Descartes' rule of signs says if you have a polynomial in one variable and you look at the sequence of its coefficients and ignore any coefficients that are zero, that aren't there. So just look at the positive and negative coefficients written in order. And every time there's a sign variation or a sign change from plus to minus or minus to plus, you count one. So you count the number of sign variations in the sequence of coefficients. And that number, Descartes claimed, proved might be an excessive statement, Descartes claimed was equal to the number of positive roots plus perhaps some non-negative integer. So this is Descartes' law of signs. If you take a polynomial f in one variable, doesn't matter what the degree is, say degree n, with real coefficients, if it has exactly p strictly positive roots counting multiplicity, and you look at the sequence of the coefficients of the polynomial, you let v of f be the number of sign changes in this sequence. And Descartes' theorem is that the number of sign changes is the number of positive roots plus an even number. I don't know if it's the first really good proof, but it's a beautiful proof. It's due to Gauss, which I wrote up at some point. Though it's better to read Gauss. And if you take this polynomial f, which has p positive roots, and you multiply it by any polynomial g, non-zero, the product fg is not going to have fewer roots. So it's going to have at least p roots also. And so the number of sign changes, again, will have to be at least p. We say that, I mean, there's some polynomials that certainly have no positive roots. For example, if all the coefficients of the polynomial are positive, and if you plug in a positive value for x, you get a positive number. So a polynomial g, we say it's a polynomial with positive coefficients if all of its non-zero coefficients are positive. And A non-zero polynomial with positive coefficients has no positive root. If you look at the set of all polynomials with positive coefficients, that's closed under multiplication and addition. It's called what sometimes it's what is sometimes called a semi-ring. And as in everything else, nature abhors a vacuum even when the vacuum is good. But there's a large literature on these so-called semi-rings. But that is the term of art. Now, Poincare somehow was perturbed by the fact that Descartes' theorem doesn't give you, if your polynomial has p roots, Descartes' theorem doesn't tell you it has p roots. It tells you that you have p plus an even number, or that it gives you the number of variations in the coefficients is p plus some non-negative even integer. So in particular, if your polynomial has 0 positive roots, then if you look at the number of sign changes, Descartes' theorem says it's an even number, a non-negative even number. It'd be nicer if it were 0, right? So there's this strange theorem of Poincare, which says the following. Well, actually, there are two theorems that I'll state. He doesn't express it like this, but this is what he proves. That f be a polynomial degree n with real coefficients and no positive root. So in that case, v of f, which is the number of sign changes in the coefficients of the polynomial, all you know is some non-negative even integer. Now, if the world were nice, it would be 0. V of f would be 0, right? For example, if you take a polynomial, all the coefficients are positive, there is no sign change in the coefficients, there is no variation, and v of f is 0. But in general, if there are no positive roots, all Descartes' rule of sign says is the number of sign changes is a non-negative even integer. So what Poincare proves is there's a non-zero polynomial g with positive coefficients, so that if you multiply f times g, that polynomial has 0 sign changes. In fact, that means that f times g becomes a polynomial with all positive coefficients.
But by what you showed us last week, it should be possible to take g to be x plus 1 to the k, right?
That is correct. But
they can make it very special form.
Yes, but right, that's Polya and not Poincare. So, but just this is quite remarkable. I think if you have a polynomial and you don't know whether it has any positive roots or not. You look at Descartes' rule of signs, you get a non-negative even integer. If it's positive, all you know is you either have 0 roots or a positive number of roots, but you don't know that you have no roots. But somehow there exists somewhere a polynomial g such that when you multiply f times g, you get a polynomial, all of whose roots are positive, and so the number of variations is 0. So
you meant all of the coefficients are positive.
Sorry, yeah, all the coefficients are positive.
The roots are not positive.
No, sorry, thank you. The number of all the it's a polynomial with positive coefficients. So in that case, that's sort of a kind of a certificate that f has no positive roots. So you might think for a minute how to prove that, and yeah. So this is all right. So this is the first result that I'm going to show. If you have a polynomial with no positive roots, you can always multiply it by a polynomial g such that the product has only positive coefficients. So the Descartes number v of f times g is 0. And then there's another theorem, this is Poincare, which says that you have a polynomial degree n with real coefficients, and let's say it does have positive roots, and counting multiplicity, it has exactly p positive roots. So by Descartes, the number of variations in the coefficient sequence of f, the polynomial f, will be p plus this nu sub f, which is some non-negative even integer. All right. It's not P. It's P plus something. And there is some contortion in the literature, which I haven't yet understood, which describes so-called virtual roots of the polynomial f, such that this Descartes number really counts the number of actual roots plus virtual roots. But whatever it is, I don't. But in any case, Descartes, Poincare seemed to be a little bit perturbed by this new f number there, which shouldn't be there, right? I mean, the answer is P. It's not P plus an even number. So again, Poincare proved that there's a non-zero polynomial K of X. K of X does not necessarily have only positive coefficients. All we can say is there's a non-zero polynomial K of X such that if you multiply F times K, so F already had P roots, so Fk is not going to have fewer roots, but in fact, it could have more, but in fact, there's a K such that F times K, the Descartes number, the number of sign variations in the coefficient sequence is exactly P. So in particular, K has no positive roots. Yeah, so if F has exactly P positive roots, you can multiply it by a polynomial K such that there exists a polynomial K such that F times K has this Descartes number equal to P. Right? So that's Poincare's theorem. Right? So the proof uses high school algebra. Actually, it's just a little bit of trig, basically. So if at some point in your childhood, you were forced to master the art of constructing and proving trig identities, that technical skill, obviously mastered by Poincare, as you will see, is exactly what you need to prove this theorem. So, and I apologize that this is just now a lot of text that is on the screen, and I will just sort of walk through it a little bit slowly. So we start with this polynomial f with real coefficients, and with that lambda be the set of its zeros, real and complex. And for each lambda, which is a zero of the polynomial, mu lambda is the multiplicity of the zero. Now, some zeros, of course, are complex. And if lambda is a complex zero, alpha plus I gamma, then so is this complex conjugate. So I can just take the complex zeros for which the imaginary part gamma is strictly positive, and then the complex conjugate alpha I minus I gamma. So here the imaginary part is negative. So if we take the polynomial x minus lambda times x minus lambda conjugate, so these are both roots of the original polynomial, capital F. If you multiply it out, you get x squared minus 2 alpha plus the square of the norm, which I'll call beta squared. So beta is the square root of this number, which is strictly bigger than the absolute value of alpha. So associated with every pair of complex conjugate zeros is this quadratic polynomial with real coefficients, and the alpha and beta satisfy this inequality. Lambda, capital lambda, is the set of all the zeros of the polynomial, so I partition it into 4 sets. Lambda 1 is the non-negative real zeros. Lambda 2 are the complex zeros whose I'm already with positive imaginary part, and where the real part is less than or equal to 0. Lambda 3 is the complex zeros with real part positive, and lambda 4, which is what I'm interested in, are the strictly positive roots of the polynomial f. So
you haven't partitioned the set of roots. You left out all the ones in the lower half plane.
Sorry.
Conjugates.
Yes, thank you. So
they're the conjugates of.
Right.
Yeah.
So it's not true that lambda 1, lambda 2, lambda 3, and lambda 4 partition lambda. Thank you. It's basically exactly what I wrote here. If I associate with each of these sets a polynomial, so lambda 1 are the non-positive roots, and I look at x minus each root to its multiplicity. These are complex non-real roots, and I look at the product of each root and its conjugate to its appropriate multiplicity. And lambda 3 and lambda 4 are defined in similar ways. Then,
Yeah, so these formulas aren't strictly correct either. They need to, the middle entries in the second and third line need to be amended. Yes. Right?
no,
No, oh, because you defined F lambda for, right, okay, fine, so that's
right,
good.
no,
Yes.
that's okay. But I should
Okay.
have said that F is monic. Right, because when I multiply these polynomials together, the leading coefficient is 1. So I need to say that F is monic, and thank you. By the way, I really appreciate when you tell me I wrote down something wrong, because everyone knows you can read your own paper 100 times and find 100 mistakes and miss the other 100 mistakes that you just passed over. Okay, so now, and notice in lambda 1 and lambda 2, the alphas are all less than or equal to 0. So if you look at this, if alpha is less than or equal to 0, F1 is a polynomial that has all of whose non-zero coefficients are positive. Similarly, if alpha is less than or equal to 0, this polynomial F2, all of the coefficients are positive. So F1 and F2 are polynomials with positive coefficients. But F3 is different. In F3, alpha is strictly positive, so this is minus 2 alpha, it's negative. This polynomial in the parentheses has negative coefficients. I don't know what happens when you multiply it out necessarily.
Yeah, it has negative coefficients, but contributes no positive roots. Yeah.
Right. Yes. Yeah, no, these are the F3 comes from the non-real complex roots with real part positive, right? So alpha is positive, so minus 2 alpha is negative. So there's a negative coefficient in there. Now, this is the part that is at the moment troublesome, this negative coefficient. That's why the polynomial F might have some negative coefficients. So I want to somehow get rid of this negativity. So recall in this set, so it's F3 that I want to focus on. That is the roots alpha plus gamma I, where alpha and gamma are both strictly greater than 0. So, and recall, beta is the norm. It's the square root of alpha squared plus gamma squared, which is strictly greater than alpha because gamma is positive. So if I look at alpha over beta is between 0 and 1. So there is a unique angle phi between 0 and pi over 2, such that the cosine of phi is alpha over beta. And if I start looking at, so phi is less than pi over 2. So 2 phi is less than pi. And maybe 3 phi is less than pi and 4 phi is less than pi. But at some point, there's some number n such that n times phi is less than pi, but n plus 1 times phi is greater than or equal to pi. So I choose this unique integer n that satisfies this inequality. Now, because phi, 2 phi up to n phi, because those are between 0 and pi, the sign of each of these n angles is positive, but the sign of n plus 1 phi is going to be less than or equal to 0. That is, I have the sign of n plus 1 phi is less than or equal to 0, because this angle is between 0 and 3 pi over 2. But for k from 1 to n, the sign of k theta is positive. Okay? Well, that's true. So we look at the following not obvious polynomial. So remember, let me just go back 1 second. Remember, I have a root alpha plus gamma I, and beta is the norm, the absolute value of lambda, right? So beta comes from this complex root. So here I have this positive number beta, sine theta, sine 2 theta, up to sine n theta. Those are all positive. So what I've written down is some trigonometric type polynomial, or it's a polynomial in x of degree n minus 1 with positive coefficients that are somehow trigonometrically defined. And every one of these coefficients is positive. All right. Now, I hid the work for a moment because it's a calculation. I'll show that at the end. From lemma 1 in the appendix, that's a couple of pages on, there is an identity. It says if you take f lambda times g lambda, right? This is f lambda, right? So lambda is the complex root with alpha, beta, gamma, alpha, the real part, gamma, the imaginary part, beta, the absolute value. So this is f lambda. And this bizarre looking thing is g lambda. And there's a trig identity proved by Poincare that says f lambda times g lambda. There's a lot of cancellation when you multiply out those two polynomials, and you end up with just 3 terms. You have a polynomial of degree, so sine n phi, remember that's a strictly positive number. So this is a polynomial of degree n plus 1. It has x to the n term, and it has a constant term. Beta is positive, sine phi is positive, so this is positive. Sine n phi is positive, so this is positive. Sine n plus 1 is either 0 or negative. So this coefficient is either 0 or positive. So f lambda g lambda has positive coefficients. And if you take all of the g lambdas and you raise g lambda to the multiplicity of lambda and you multiply this together, this is a product of polynomials with positive coefficients. So g of x has positive coefficients. And yeah, g of x is positive. And what is f3 times g? Remember, f3 was the product of the f lambdas. So the product of the f lambdas times the product of the g lambdas. That's the product of powers, powers the multiplicity of f lambda g lambda. This is a product of polynomials with positive coefficients. f3 times g is positive coefficients. f1 and f2 to begin with are positive coefficients. So if I let L of x be f1, f2, f3 times g of x, this polynomial has positive coefficients. Now, I haven't said anything about lambda 4. Lambda 4 was the set of positive roots. If there is no positive root, if lambda 4 is empty, then f of x has no positive root. f4 is equal to 1. So f of x is f1, f2, f3, and this polynomial L of x is f times g. So this proves the first theorem of Poincare, right? If f has no positive root, here I've constructed very explicitly, actually it's very explicit. I mean, sorry, it's not really, it's explicit if you know the roots. God knows what the roots are, but there exists this.
Well, you can say some very definite things about it, right? There's no upper bound in terms of the original degree. The closer the root is to the positive real axis without being on it, the higher the degree we're going to have to take.
Correct.
If you're very, very close to the real axis without being on it, n is going to have to be very, very large. Yes. You can get it arbitrarily large. So you can say that.
Right. Yes, you can say that, but
negative. It's a negative sort of result.
If someone gives you a polynomial f and tells you that it has no positive root, I don't know from that how easy or hard it will be computationally to find an upper bound for the degree of this polynomial capital G. So
you mean without actually calculating the roots?
Yes, which of course, you can't do, but
well, you can do it numerically and get some approximation.
Yeah, you can. Yes, you're right. Okay, so if there is no positive root, then f1, f2, f3 is equal to my original polynomial capital F. F times g has positive coefficients, and the variation in sign of f times g is 0. So that proves Poincaré's theorem, theorem 1, right? The case when there's no positive root. So let's now consider the case where there is a positive root. That is, lambda 4 is not empty. So I have this polynomial L of x. L of x is f1, f2, f3 times g. This is a positive polynomial, all of whose non-zero coefficients are strictly greater than 0 or positive. And let's say this has degree q minus 1. Now, for every alpha that is a positive root, take the polynomial h alpha, which is x to the q minus alpha to the q over x minus 1. It's this polynomial of degree q minus 1.
Yeah, you meant x minus alpha, of course, what's written, not x minus 1.
Yeah, sorry, yes. X to the q minus alpha to the q over x minus alpha. Exactly what I wrote. So, and take h of capital H of x to be each of these polynomials raised to the multiplicity of mu of alpha. So if I take f4 times h of x, what was f4? F4 was the product of all the positive roots alpha, x minus alpha to the mu of alpha. And I multiply this by capital H of x, which is h alpha of x to the mu of alpha. So that's x minus alpha, h alpha to the mu of alpha. That is exactly x to the q minus a to the q to the mu of alpha, right? So m of x is this polynomial. And if you expand this, this is a polynomial in powers of x to the q, right? So this is a sum of, well, I say powers of x to the q. Those are the powers of x that occur there. And what is the number of sign variations in this polynomial? So I say by lemma 2. So what lemma 2 just says, so forget about x to the q. Suppose x to the q were just x, and alpha is positive. So this is like a product of linear terms, x minus ai for a lot of positive ai's. And if you multiply that out, that's an alternating, you get an alternating sum of powers of x, strictly alternate, every plus minus, plus minus, plus minus. So the number of sign variations in this polynomial, that is capital V, this is the Descartes rule of signs number, the number of sign variations is the degree of this polynomial, which this should be, it's just a typo here. This is just the sum over all alpha, the multiplicity of alpha. That's equal to P. That's the number of positive roots of F counting multiplicity. So the number of sign changes of M is equal to this number P. And oh, lo and behold, I claim now I've proved Poincaré's second theorem. Because if I take, let's see, the original polynomial F times capital G, that's this guy up here, times this polynomial H. So what is that? So F is F1, F2, F3, F4 times G times H. F1, F2, F3 times G, that's this polynomial L, and F4 times H is M. So I'm multiplying L and M. Now, let's look at that for a second. M is this polynomial which only involves powers of x to the q. And there's some variations of sign in the coefficients of that. It's not all positive coefficients, certainly. They're variations of sign. In fact, we know exactly how many. They're p variations of sine. What happens when you multiply this polynomial by L? So L has degree at most q minus 1. So whenever you have a term like x to the 3q, let's say, times L, you're going to get a series of terms, which is like that x to the 3q plus 1, you're going to have increasing powers of x, and the coefficients will be what was originally the power of x to the q times a coefficient of L, but they're all positive. So it's like if you have a positive coefficient here, you just like stretch it out into a string of positive coefficients. And then you come to a negative coefficient and you stretch it out to a string of negative coefficients. But that doesn't change the number of sign variations in the sequence. That stays the same. So the number of sign variations of Lm is exactly the same as the number of sign variations of m, which is p. So let me call GH a polynomial capital K. So V of f times K is V of f times GH or Lm or m or p. And that completes the proof of Poincare's second theorem. Okay. Now, the crux of this was that trigonometric identity. So I call this appendix 2 identities because there are actually 3 identities, but that's all right. Remember, I had a polynomial that looked like this. I don't care about the signs. I don't care whether the number beta is positive or anything. And I don't care what the sign, the SIGN of these trigonometric sign things is. Here I have a polynomial, x squared minus 2 beta cosine phi x plus beta squared. And I have this polynomial whose coefficients involve powers of beta and the sign of multiples of phi. And I claim if you multiply these out for any number beta and any angle phi, you get exactly what I claimed you got. And again, if you want to look back to your nostalgic days in high school, where you learn things like the addition formula for the sine, right? Sine of k plus 1 or sine of k minus 1. Well, you get these formulas. If you add them up, you get some cancellation. You get something like this, and you have a double angle formula for the sine, and you get something strange that says sine of n plus 1 phi is sine. This is like the addition theorem, and then you play around and you see you get this, and somehow you put it all together. And so you keep these in mind. You have to remember these identities. So this was F and this was G. And when you multiply it together and you collect the terms, you get some humongous mess. So you have a constant term, a linear term. You have the x to the n term and the x to the n plus 1 term. And then you have all the terms from the powers x to the k from 2 to n minus 1. So for example, for the linear term, when you collect everything, the coefficient is sine 2 phi minus 2, this is just another typo, minus 2 sine phi cosine phi. That's 0. That's just the double angle formula. Here, you get something like, so for all these x to the k terms, you have a power of beta, and then you have sine k plus 1 phi minus 2 sine k. You have this relation, which that's this. It's 0. So everything cancels, right? Now, I know in our sophisticated age, we would say it's beneath a mathematician in the 21st century to use trig identities. And by, reductio ad absurdum, you might say, so obviously, even in the 19th century, a mathematician, a great mathematician, Poincare, would never demean himself by using trig identities. And I have to say, that's true, because Poincare doesn't prove this. He just states this as a fact. You know, it's just poor schmuck like me who has to go and figure out why this is true. But obviously, Poincare knew his high school trig identities, and you know he just didn't bother to write this down. But this is, in fact, right here, the key identity, which is the identity that that he uses. The other sort of identity that I use in the proof said something like this: if you have positive numbers a sub I, and again, this exponent m shouldn't be there. This is just the product I goes from 1 to m of x minus ai. The number of sign variations in this is m, and the one-line proof, well, it looks like 3 lines, but it's really 1 line. I want to know the number of sign variations in this. It only depends on the positive or negative sign. So sign of ai is 1 or minus 1, depending on whether ai is positive or negative. And these are all positive. So this is just x minus 1 to the m, which, you know, that's just the binomial theorem. You expand it, and you see exactly the sequence of coefficients is 1 minus 1, just the alternating sequence of plus and minus 1. So it's exactly equal to m. That's the proof. And then the third identity.
Sure about this? Are you sure about this first line of the proof?
Am I sure about it?
Yeah.
Well,
I mean,
I actually had a different proof, and a few minutes before I logged on at 2:30, I said, "Oh, I can do it in 1 line like this." And
well,
are you saying that the AIs might cancel somehow? I don't know.
I mean, it's certainly not obvious to me that this statement is true. I need to think about why it's true. It's not something that I see all at once.
Right. No, you make, as always, a very good point. So it is certainly true. If you multiply, I'm going to worry about that.
I accept it's true for all the AIs positive. Okay, I'm sure that's true.
Oh, well, that's the only case I'm considering.
Of course,
AI is greater than 0.
I know the statement is true. I'm just wondering if the first line here would be true if it weren't the case that the AIs were all positive.
Yeah, I don't know. I would think about. I have to think about that. But
okay, same here.
I mean, I was just thinking when these are all positive, and then any you're taking uniformly sums of products of positive numbers, and it's always positive. So this is certainly correct with the AI is positive. So there's not going to be any cancellation or sign change in the middle. So this is okay. All right. Now, so that's the end. That's Poincare's little paper. It takes about a page and a half in the compte rendu. And you might wonder for a minute about Polya's statement that, because remember, Poincare is proving something about polynomials in one variable, and Polya says that is evidence for his general theorem about homogeneous polynomials in several variables. And he says that what Poincare has done is prove the case for him of homogeneous polynomials in 2 variables. And Poincare and Polya's theorem says if you have a homogeneous form in n variables, which is strictly greater than 0 everywhere in the non-negative orthant, except for 0. Sometimes the orthant is called the octant. The octant is really like in 3 dimensions when it's 1/8 of the space. And sometimes people use octant for higher dimensions, but Ashwin made a point of telling me that orthant is a better term to use. So I switched from octant to orthant. Sometimes people are lazy like me and even just say quadrant. But in any case, so you have to think for a little bit about how Poincare's theorem about polynomials in one variable is equivalent to Polya's statement about forms in 2 variables. And
You mean the passage from non-homogeneous to homogeneous?
Right.
That's sort of
mean,
standard. And
Yeah, there's a standard way. You take your polynomial in one variable and you throw in a second variable and you make it homogeneous of the
although
same degree.
it's still not the same. It's still not the same thing, is it? Because Polya uses a particular G, a very particular G. And over here, we didn't, our G's were sort of redesigned for each set of roots.
Right. So that's true. And so it really is that what Poincare is giving for for binary forms is the existence of a polynomial G with positive. So what is relevant to Polya is what I separated out from Poincare's note and called theorem 1, the case where there is no positive root for the polynomial. And in that case, you get a polynomial G where f times G has strictly positive coefficients. And so that is, if you like, evidence for that may be suggested that something might be true in general, suggested to Polya that something that might be true in general. And in fact, Polya's theorem is stronger because it gives you the form of a polynomial. It's x1 plus x2 up to xn raised to some power capital N. And various people have given explicit estimates for capital N for the exponent. And in the slightly revised version of my notes on Polya's theorem, I write down something explicit. Not the best, but I have to confess, in the world of analytic number theory, people love to improve exponents, and you often have to do a lot of very hard work to, improve the error term of something. For me, most often, I'm happy to know there's some explicit error term exponent, and making it better doesn't usually thrill me because I don't need it for anything. I'm just happy to know there's something explicit, perhaps. But in any case, there is a literature on Polya's theorem trying to make it explicit. There's another question about Polya's theorem, which I thought might be trivial to prove, and it may be, but it's slightly less trivial than I would guess, which is in Polya's theorem, you might remember, you take your homogeneous form in n variables that's positive in this non-zero, non-negative orthant, and you multiply it by x1 plus x2 up to xn to a power, and you get a polynomial, you get a form which is positive. All coefficients are positive. But suppose instead of x1, suppose you tried to multiply it by, let's say, 2x1 plus x2 plus x3. Or, instead of the linear form, which is the sum of the n variables, some summation ui xi, where the ui's are positive. Does it still work? And
I'm pretty sure that by a change of variable, you could show that it does.
So that's what I tried to do, exactly.
And it isn't that simple?
Well, I worry about things like the point you made with a moment ago about the AI, the x product of x minus AIs. So maybe when you plug in, remember, you're not multiplying each variable x by the same number u. If that were the case, it would be fine. But you're replacing, so you have f of, let's say, x, y, z replaced by f of 2x, 3y, and 17z. And your polynomial, you'll recall, that you start with does have some negative coefficients. So it's not obvious that when you make this substitution, it still is positive definite. I see Dick shaking his head as if he knows for sure it's not positive definite.
The whole
So,
thing is based on the fact that if you take a simplex that avoids the origin, that you get values that are bounded away from zero there. And it doesn't matter where that simplex is.
oh, so you're saying it is obvious.
Yeah.
Uh-huh, okay. So,
And another point, your trigonometric identity could probably be proved more simply using complex exponentials.
yeah, that I understood, but I was trying to keep it in the spirit of Poincare, who wrote everything down with sines and cosines. So, yes. And I will say, I felt a little bit proud of my knowledge of 9th grade or 10th grade high school math, that I could remember some of these trig identities and work it out. So, yeah.
Well, I was a little bit puzzled by the first remark of Poincare concerning Laguerre. I mean, Laguerre worked with exponentials, and maybe Poincare tried to figure out, instead of using the exponentials, to use Euler's theorem about cosine and sine and the exponential. There may be some direct line between Laguerre and Poincare, but it's not clear to me without thinking a little bit more carefully.
Yeah. So you and I have referred to Laguerre's theorem, but it's never been discussed in the seminar. I don't know, Carlos, whether you would be interested in giving a talk on Laguerre's paper.
No, not this time. No. You probably said as much as I went to think about it. But it's an interesting theorem of Laguerre.
Yeah.
But this question of going from the exponentials to the polynomials, it's in the background. I mean, that's it would be worthwhile thinking about it, but not for me at this time.
Yeah. I must confess, though, I find it a lot of fun to dig up these old papers and try to figure it out. Sometimes, if it's really old, it's not a question of the language. It's just the terms that are used are just don't fit into the context that I know. Sometimes it's really hard to read an old paper, even if the result is like in every freshman calculus book.
Yeah, group theory is worse. In group theory, there was a shift in, mid-20th century, I guess. So a paper from 1904 can be almost unreadable. Yes.
Yes.
Yeah. The German terminology is being more or less literally translated, I guess, and it can be very hard to follow.
Anything else new in the world? I will recommend again that everyone check the website of the School of Mathematics of the Institute for Advanced Study and click on resources to see the videos of the 15-minute lectures, which tend to be 20 to 25 minutes, of the postdocs at the Institute this year. And you can, like for 20 minutes, you can see something very interesting often. And lots of things being discussed this year are related to topics that have come up in the seminar in the past. So it is a very good resource.
Definitely. Yeah.
And in fact, if anyone is interested, there's a guy named, I think his name is Richter, who might have been a student of, what's the ergodic theory guy at Ohio State who generates all of naught students and papers a year?
Bergerson?
Sorry? Yeah, Vitaly Bergelson. So he has a student who's giving a talk, I think, at 4 o'clock in about 7 minutes. A 15-minute talk on something that is sort of additive combinatorial and might be interesting. Florian Richter.
Check it out.
All right. Any other comments or questions before we decamp? Okay. Okay, everyone. Have a good week. Be back next week in some form.
Yes.
Take care.
All right, bye.